I'm always optimistic on that front, and I guess I say that because I've been doing that research now for 15 years or more, convincing myself that we know where the resources are. We know mines can be developed quickly when all of the different factors align. Now, the questions really then come back to, well, how do we make sure we get those factors aligned? Now, one of the biggest concerns for communities in looking at rare earth mines and also rare earth refineries is how are all the radioactive residues managed. So I think the world can achieve things when we set targets and we work towards that. Now, we can and we will because we have to. The issues around climate science and so on shows that things are getting worse all the time. So
Picture this: a guy who looks at a pile of rocks and sees the entire future of energy, technology, and possibly the fate of human race. That's Gavin Mudd, ladies and gentlemen. As a director of critical minerals intelligence center, he's the Sherlock Holmes of the mineral world, solving supply chain issues, mysteries, exposing hidden risks, and making sure we don't run out of stuff that powers everything from your smartphone to electric car. Gavin has spent his career turning boring into brilliant, breaking down complex assessments of cobalt, lithium, and even iron. Yes, iron made the critical list, like it's the plot twist of a blockbuster. He's here to talk about what makes materials tick, why recycling isn't just for hippies, and how can we keep the world running without accidentally blowing up the supply chain. Gavin, welcome.
G'day. Pleasure to be here.
Can you give us a short introduction into who is Gavin Mudd?
Sure. I'm an environmental engineer by trade, I guess, and I often consider myself a generalist. My experience, I suppose, my career started in groundwater. It's something I've always kept a close interest in. But when I was doing my PhD, what I realised is I was getting a PhD for understanding the impacts on groundwater from one side. What about the rest? How do you start to think about an entire industry and their performance in that way? And so I started thinking about that and looking at that and saying, well, how do we really assess the sustainability of mining, not just at an individual site level, but at a whole level? And so after I joined academia, I suppose I started working on sustainable mining, looking at the issues such as declining ore grades, increasing mine waste and mine rehabilitation, impacts on groundwater, all of these things. And that led me to sort of start collaborating with Tom Gradle, who sort of, I suppose, appreciated the work. And he was, at the time, this is going back into the 2000s, was looking at the periodic table and thinking about critical minerals and thinking about he was involved with the National Academy study in America looking at critical minerals that really was the modern Kickstarter to all of that. And when you're looking at the data for a lot of the technologies that we use, we don't have much data. We don't have reserves data, for example. Like the USGS regularly updates their reserves estimates globally for things like iron and copper and gold, and a whole range of the periodic table. But for many of the technology critical metals, we don't have that sort of assessment. And so one of the concerns Tom had was actually, well, where are we going to find the reserves for germanium, for indium, and all of these other things that we need in increasing quantities? So, and I guess that was where I started. And I'm thinking, well, we know we've got plenty of copper, and if we get tellurium from copper, then we must be able to be confident about whether it's tellurium or if we look at indium from zinc, for example, we may not have detailed deposit by deposit data for indium in every zinc deposit, but we do have that data for zinc. So since then, I guess I've been doing a lot of work, putting those sorts of data sets together and really addressing those questions about, do we really have the resources? And I'm absolutely confident we do. And I think when you're looking at a lot of these things, the bigger issues are not just the amount that we have, it's the broader environmental constraints, the social constraints, the geopolitical issues. And that's, it comes back to full circle, looking at the environmental side of things and understanding all of these types of things. So that's sort of, I suppose, my career in a nutshell.
I can already see this will be an interesting one for sure. Can you provide an overview of how criticality assessments are conducted and the key factors that determine a mineral's criticality?
Sure. Criticality is really a way of actually quantifying in an objective way as best one can what's important and why. Now, if we, let's say, for example, the US didn't have access to oil, that would have huge implications. So we would rate oil obviously very, very critical. Now, by the same token, we could look at, let's take platinum for example as the sort of the quintessential example. A lot of the world's platinum, the majority, is generally mined in South Africa. Now, in a post-apartheid South Africa, there are always concerns about the sort of the stability of that country. If we didn't have platinum, flowing globally, then wouldn't be able to maintain the catalytic converters in our current combustion vehicles, and that means our urban air quality would get really bad again. Right, it would take us back 50 years effectively. So when we're looking at things like platinum, we're worried about where it comes from and that supply, but then we're also worried about the impact that that could have. And so and that's really how we mold together criticality assessments. We're worried about the reliability of that supply, and then we're worried about the potential impact if we have a supply disruption, or if that supply becomes unavailable for all sorts of different reasons. Now, that's the sort of starting point. People around the world, including academics like Tom Gradle and others, but different groups, whether it's sort of at a government level. Sometimes companies do their own criticality assessments as well to understand their own supply chain. So, largely what we're trying to factor in when we're looking at supply, it's largely which countries are the dominant suppliers. And so, if you're looking at platinum, it's about 60% South Africa and a bit from say Russia, Canada, and the US and Zimbabwe. But then when you're looking at other things, it's like, well, indium at the moment is produced a lot in China, but that's only mined or extracted when you've mined zinc. So that companionality, or as it's often called, or companion metal fraction, becomes really, really important in looking at supply too. So that's something we've certainly incorporated. And so looking at how much of something is reliant on the mining of something else. All right. And so that applies to a lot of our technology metals, actually. So other factors that people may or may not look at include global trade, whether it's net imports or things like that. Recycling rate is often something that's used. There can be different factors applied to these things. So you could take, say, the World Governance Index from the World Bank and use that as a whole, or use parts of that as a way to look at issues such as violence or corruption as part of governance. There's all sorts of things that could be incorporated into looking at global supply, but typically the most important one is always the countries that are dominant in that supply of that particular metal or mineral. The economic impact side, or vulnerability side, as it's often called, is really trying to unpack, well, what's the scale of that impact that could happen? So if we're looking at something like let's take the gold sector, for example, you'd be looking at an extremely valuable amount of economic activity related to gold. And so if there wasn't access to gold, then that could cause very significant impact, both financially as well as to our electronics and things that use gold. So, so when we're looking at the economic side, we often look at the amount that's consumed, right? And so with gold, it may not be a large amount by mass, but by value, obviously, is very, very high. So then we're looking at other factors that may or may not be incorporated into that value, whether it's the economic sectors, the end users, trade barriers can sometimes be incorporated. They can be difficult, but all of these things come into that sort of economic vulnerability, and that's how we sort of meld that together and so on. And other people sometimes may include environmental aspects or social aspects, and come up with
Yeah.
about a third axis as well. But typically, most groups tend to use just the two primary sort of axes of global supply risk and economic vulnerability.
How has this methodology for assessing critical minerals evolved over time? And, and generally, how do you get all the data?
Generally, the way the criticality assessment has evolved is looking at some of the different factors that are involved in things like supply or economic vulnerability. And so, typically, because criticality assessments are mostly done by government agencies, the process has to be public and has to be transparent. And so, a lot of the methodologies are published and out there, but the data is typically therefore public. Right now, whether you're looking at world mining statistics, so that could be the British Geological Survey's world mineral statistics. Sometimes people use the US Geological Survey as well. So generally, we're using public sources of data, and that includes a lot of trade data. And so that can be either UN Comtrade or national trade statistics or other economic statistics. Often, a lot of the industry associations are now putting out their own data sets on things like recycling rates or end use by sector, and so on. So there's generally, for a lot of things, there's a reasonable amount of generally good quality data there. But for some metals, they're very, very closed markets, and so there's not a lot of public data out there, and that's always a challenge.
Yeah. What role do geopolitical factors play in influencing criticality, particularly for minerals sourced from politically unstable regions?
Generally, the supply, part of the recognition of the global supply risk is geopolitics. It's the concerns around whether it's the stability of a country. The Congo, of course, is often a classic example when they had civil unrest emerge in the late 1970s. That sent the cobalt price through the roof. And so the aerospace industry at the time, which was one of the biggest consumers of cobalt, went to substitution, and so they went to different alloys, but that also shut down cobalt supply almost completely for the best part of 20 years in the Congo. So geopolitics is always a big driver. The other thing, of course, around that is not only just the countries that actually where the production comes from, but also who controls that production. Increasingly, of course, we're seeing China playing a very, very dominant role, not only in just the production and extraction from smelters and refineries of a lot of these byproduct metals that are companion metals, but also their control of, say, cobalt in the Congo and say nickel in Indonesia. And so that's one of the concerns around, at the moment, is that China has been sort of certainly positioning itself very well in this regard, and so that's part of the geopolitics is the who controls those supply chains, and as well as just the whether it's political stability. I guess about 5 years ago, I was scheduled to go to Santiago. Literally, 12 hours after I booked my flight, there was the news emerge of the riots occurring in Santiago, and so that trip got cancelled very quickly. But and that really shocked the global mining industry because Chile was certainly seen and had evolved to be a very progressive country, and clearly, there were very serious issues that certainly a lot of the population felt weren't being addressed properly. So, hence the sort of civil unrest there. So that really caused concerns around the stability of Chile as a country, and I think they've sort of moved forward from there. But again, that's part of geopolitics and understanding things.
I think that's very interesting field for the future of materials and generally the energy. And is there a kind of workaround for that?
They're not easy. There's all sorts of workarounds that people talk about. Some are investing in different places to make sure you've got a diverse supply chain. That takes time. Substitution, you often have to accept poorer performance, and so substitution it can be done, um, but it's not always easy and it takes time. But with research, then you might be able to find maybe even a new material or a new way of doing things that uh, still achieve the same performance or better, perhaps. And certainly, the electric vehicle battery space is a great example of that, with the move very strongly towards lithium iron phosphate batteries that avoids the cobalt problem and nickel and so on. But it then creates recycling problems because the battery is so much cheaper, and therefore the value to pay for recycling is just not there in the same way it was, say, with cobalt and nickel in the battery chemistry. So um, other things are looking at different trading partners. Now, when you've got situations such as Rhenium, for example, where you've got one company even that controls 70% of world rhenium supply, then that's not easy to just diversify away from. So a
Mm.
lot of the different ideas, policies that have been put in place, none of them are easy. None of them are generally quick. But that's part of the problem is we need to make sure we're playing a really long game here and actually really thinking about these things much more strategically rather than on a very short-term basis.
Very interesting. Uh, could you elaborate on inclusion of ESG factors in criticality assessments and their impact on decision making?
Sure. Coming from, I suppose, the environmental side of mining, when you're looking at mining globally, we know mining has a bad reputation. It causes impacts. Now, when we have good environmental management, we can reduce those impacts, very, very significantly. And we see that in countries, whether it's well-regulated countries like Australia and elsewhere. Uh, but that's the concern. They're certainly coming from many parts of the world that don't have the regulatory and sort of governance sort of processes in place to make sure that mining is actually occurring in ways that are not causing bad environmental impacts and social impacts and so on. So when you're looking at your phone or your car or laptop, we want to make sure these days, and I think it's a noble ambition that when we're mining and we're producing the materials that support all of our different technologies and infrastructure, that that material is responsibly sourced. And that means that really we have to deal with our environmental, social, and governance factors, and that means when we're looking at whether it's cobalt, whether it's platinum, whether it's whatever metal, that it is being responsibly produced. And so that's the great challenge at the moment is you've got across the world an enormous range of different standards and impacts. And so we don't want to be repeating those mistakes of the past. We want to be making sure that future supplies really do build in that responsibility. And so that way we can be confident that when we've got whether it's our renewable energy, whether it's our technologies and our infrastructure, that it is actually helping move the world forward, whether it's sustainable development goals or other ways to look at it. But that's really why we need to be making sure that we do incorporate ESG not only just into the way we do a criticality assessment, and there's various methodologies for doing that, but from a policy point of view, that's certainly very, very important because we want to make sure that we're doing things right and making sure we're contributing to responsible development going forward.
Yeah, that's true. So, what are the realistic chances? And we're now going to the hot topic of the day uh, of meeting global renewable energy transition goals within current timelines concerning the critical minerals.
Yeah, I'm always optimistic on that front, and I guess I say that because I've been doing that research now for 15 years or more, convincing myself that we know where the resources are. Um, we know where the zinc resources are that contain indium, for example. Although we don't have great data on indium, there are methodologies that we've developed, and I've had some wonderful PhD students over the years, so we can be confident the resources are there. We know that when we're looking at global resources, we're not worried about resource depletion. We really aren't. And I know there are some scholars out there that do argue that we're getting close to resource depletion, but we know of more resources now for everything that than we've ever known before. So uh, the question is, where do we mine? How do we mine? What do we mine? And then ultimately, who controls that mining? So I think when we're looking at the overall picture, I don't see any resource constraints just from a geological point of view. The questions really relate to actually the standards of how we mine, such as the responsible mining. That's part of the reason I guess I've always advocated for the initiative for responsible mining assurance. I think that's the best standard out there for demonstrating responsibility in operating a mine. So it comes down to understanding, well, how quickly can we develop a mine, and certainly mines can be developed very quickly when all of the when everything lines up. In Australia, we've developed between 2015 to 2019, we went from one lithium mine to nine. So mine, and most of those didn't even have a drill hole in 2015. So, and by 2019, they were some of the biggest lithium deposits in the world, such as Pilgangoora and others. So, mines can be developed quickly when all of the different factors align. Now, the questions really then come back to, well, how do we make sure we get those factors aligned? Now, in some parts of the world, you've got significant community opposition because sites are being looked at that really, I think, don't make much sense, whether it's next to a World Heritage site or Neolithic sort of heritage or all sorts of things. Uh, but sometimes we can actually work out ways where there are other places we can mine. Right now, if you're looking at the issue of rare earths, for example, part of the problem there always comes back to the radioactive nature of those ores. Typically, that's more controlled by thorium than it is by uranium, but certainly some uranium exists, and often at even economic concentrations to be able to extract that uranium. So one of the biggest concerns for communities in looking at rare earth mines and also rare earth refineries is how are all the radioactive residues managed. And I think that's one of the things certainly I've done a lot of work on over the years, that we can see our way clear on that. We know how to address that. But I think what communities are sort of certainly shouting around the world is that they don't see that those standards are being um, achieved both by existing operations or by the way the governance and regulatory processes work. And I think part of the fundamental problem with that is that a lot of the way that we consider things like radioactive waste looks at thorium and says it's got such a low specific activity, it's not really radioactive waste. Whereas the communities look at all the decay products and go, they're pretty short half lives. That means that's a significant dose. And so actually that's a real problem. We need to be making sure we're not exposing, things so that it's perpetual material. And so when we're looking at the radioactive nature of the rare earth sector, we need to make sure we're really actually addressing those sort of key concerns. And so that's that's where the challenges are, is making sure that we've got all of the environmental side, the social side, um, and making sure that we're dealing with all of those concerns, I think, head on, and that way we not causing bottlenecks, we're actually solving them.
Can we catch these deadlines that we have set for ourselves?
Absolutely. I'm very confident of that. I think when you're looking at a country like China, they set a target for renewable energy by 2030, and they've already hit it months ago. So I think the world can achieve things when we set targets and we work towards that. Now, the UK, for example, shut down its last coal-fired power station a few months ago. Now, that is epic. That is actually an extraordinary change for the country that actually brought on the industrial revolution globally, based on coal. So I think we can and we will, because we have to. The issues around climate science and so on shows that things are getting worse all the time. So I've got no doubt that we can, but it's hard. Of course, it's hard. I don't think we should be kidding ourselves in that, obviously. But I'm very, very confident that we can certainly get there without a problem. It's just a matter of keeping up the agenda, making sure we're being deliberate in our choices, and uh, yes, absolutely, we can meet the targets, whether it's net zero by 2050 or other targets for say electric vehicles and all sorts of things. So yes, I'm certainly very confident.
You mentioned wise mining, but also, are we using these materials wisely?
Ultimately, there's a lot of things we can do. Some parts of the response actually mean we should be designing our materials and our products to be smarter. Absolutely, making the materials actually the products more efficient with the way that they use materials. And industries do that. There's generally a self-interest from a lot of the companies that make different products to do that. So, and we've seen that over time. I remember many years ago when we first started looking at the actual metal content of smartphones, for example, the gold grade was around about 750 to 900 grams per ton. A typical gold mine around the world would be about 1 gram per ton. So the amount of gold sitting in a smartphone is actually extraordinarily high. Now, within a decade, that had dropped down to around 250, and I haven't checked more recently, but um, and that means that the most valuable metal in a smartphone is actually gold. So generally, when you're recycling a smartphone and similar electronics, it means that gold is the one that really pays the bills. So there's certainly a role for smarter design. There's also things such as right to repair. So rather than having to replace a whole product, you just replace a component. And I
Yeah.
think the best model I've seen of that is the Fairphone, which is out of Belgium. And so that's certainly part of it. But also putting in place policies for recycling, and making sure that the infrastructure is there as well. So things such as the waste electronic and electrical equipment sort of regulations, or WEEE as it's called, are really important, and they're part of that long term sort of shift. And so that way, as we get more from recycling, we need less mining as well. All right. But I think one of the challenges, and this is something that's certainly part of, I suppose, the energy transition, is that for many of the technologies we're building out, we don't have the stocks at the moment to provide the flows for recycling. So if we're looking at electric vehicle batteries, we've only really been, I suppose, rolling out EVs now for close to a decade, and an exponentially increasing pace. But it'll be still some time before we start to see a very large amount of EV batteries start to flow to become available for recycling. And so we need to build up our stocks in our urban systems and infrastructure and so on, to get to the point where we've got enough flowing from recycling. So we'll still need mining for quite a while yet. Now, at some point, we also have to recognize that some of the uses are actually dissipative. Antimony has been in the news this year because of restrictions in China. And a lot of people think that's geopolitics, but I think the reality there is actually very simple. It's their antimony smelters and refineries and so on in their mines were, many of them were causing very significant impacts to local communities. And so they've really tightened up their regulations around that, and that's forced the closure of over half of their antimony sector. China used to provide almost two-thirds of the world's antimony. It's now down to close to a third, I think. And so when you're looking at that, that means that when you're looking at antimony, about half of antimony is used in fire retardants. That's not something I think would be easily recyclable. So,
Yeah.
so there are different ways we use different materials that are dissipative. And they're not able to be recycled. So I think that
Yeah.
means for antimony, we'll always need to find ways of maintaining that sort of supply. So, and again, and the stories and the issues vary enormously across all the different metals and elements that we use, and the minerals as well. Noting that some things like helium, they're gases. So when we say critical minerals, and we normally mean either a metal, a material, or potentially a mineral as well, I guess. So when we're looking at, I suppose the response is that we see all of these options out there. And I guess some companies are already very good at doing that. Like you're looking at, say, the aerospace industry, for example. You don't buy a turbine anymore. You generally lease it, and then it goes back into, at the end of its life, it goes back to its manufacturer, because a lot of the high value alloys in that, and so those manufacturers can get that turbine back, and then they'll recycle it and bring it back into their system again. So there's already a lot of things that are happening. Just that sometimes the data and I suppose the wide knowledge of that is not out there yet, but certainly there's things happening.
For sure. And we will definitely touch on the topic of recycling. Uh, is there a shortage of minerals, and how can industries cope with that shortage of critical minerals if there is one?
I don't think there's a shortage of critical minerals. I think what there basically is just the geopolitics around the control of that supply. We know the resources are in the ground. We know the mines are operating, and we know the various smelters and refineries around the world that extract different things. So really, it comes down to the control of that supply, and certainly so much of the supply of technology-related metals and minerals is China. Now, China's certainly been building that position for a long time. That's their long game that they've been sort of working hard to achieve. So, and that's now giving them some quite significant advantages in there, whether it's electric vehicle manufacture or renewable energy manufacture, and so on. And so, I think, to me, I don't think there's a shortage out there. I think it comes down to these questions of supply. And we're looking at, if we take indium for example, we know that indium has almost doubled in the last decade. We know that the rate at which we're extracting indium from zinc refineries continues to increase. The rate at which we're extracting cadmium from zinc refineries is gradually declining, actually, and that's probably related to the fact that cadmium is a toxic metal, so we need to be very careful in using it and so on. But And so largely when you're operating a zinc mine, if there's too much cadmium in your zinc concentrate, um, you'll get a penalty, you'll lose money, and so
Yeah.
so mines, I think, have often been optimizing for reducing things like cadmium in their zinc concentrates and never worried about something like indium, which is only 0.1%, maybe 0.5% of the revenue if you're lucky, and that's actually if you get paid for it. So most mines, of course, and in fact, the vast majority of mines would never get paid for their indium content of any zinc concentrate. They might get paid a tiny bit for the cadmium concentrate, cadmium in that zinc concentrate, as long as there's not too much. All right. So I think when you're looking at a lot of these things, and again, the devil's always in the detail, but I think we are seeing long-term consistent patterns of increase. Now, can we increase things at the rate we need to make sure we really do achieve net zero? Well, that's debatable. And I'm very optimistic that we can, because we've certainly seen in the past, whether it's nickel, whether it's copper, aluminium, iron ore, many times we've been able to increase supply at rapid rates once we've chosen to, and all of these different factors align, whether it's the economics, whether it's the geology, and all sorts of things. So certainly we can see that. It's a good tale, I guess, is also looking at Australia and iron ore. In 1938, Australia actually banned iron ore exports. And people go, that just sounds weird, but we did. And the argument put forward was that Australia didn't have enough iron ore for its own industrial development. The reality is that at the time, the exports were scheduled to go to Japan, and that was not politically popular nor wise, especially given the next several years after that, obviously. So now that export ban was not overturned until 1960, once the Pilbara was discovered and people realised that Australia is more than blessed with iron ore. The
Mm.
problem with iron ore in Australia at the moment is that it's mostly a hematite, goethite type iron ore, and for green steel, one of the things that people are looking at is that the better type of iron ore is really magnetite. And so that's something Australia has a lot of, but it means the billion tons of iron ore that Australia now exports every year, when back in 1938 Australia thought we only had 250 million tons of iron ore reserves, and yet now we're actually exporting a billion tons a year, and we've got much more than 100 billion tons left. So even if we kept mining at a billion tons a year, we've got a centuries left of high quality iron ore left in Australia, and that's the high quality stuff. Let alone the slightly less, quality material as well that could be, quite easily upgraded and processed. So I think that there's various examples out there. So I think to me, it's coming down to these questions of, yeah, we know what the trends are, we know where the technology drivers are heading, so we can look at the scenarios and work forwards in that way. Or we could take targets such as net zero by 2050 and say, well, let's work backwards. So and work all of these things out. And so whether it's the International Energy Agency, whether it's our own work at the Critical Minerals Intelligence Centre at the British Geological Survey here, or whether it's many other groups such as the European Union and the US and so on, or Japan. China's doing this as well. So people have all looked at these different sort of scenarios and say, yeah, well, there's some we need to achieve record rates, but we've done that in the past. Like certainly, you can see good examples in the past where we've certainly achieved rapid growth rates.
What about mining in Europe? How big it is, and can it get bigger?
There's certainly a lot of different mining activity in Europe. There's whether it's say copper up in Sweden and Poland, for example. All right, um, you've also got significant amounts of lead zinc mining in different parts of Europe. So whether that be also in Sweden or down in Spain and elsewhere, Portugal, for example. I think the questions become is that Europe has a much higher population density, and Europe has also lived with the consequences of mining historically, where mining wasn't done with great environmental regulation. Modern mines are, all right, but the historic mines weren't, and so there's a lot of concerns that new mines will repeat those mistakes of the past. And that's a legitimate concern, and that's something that I think, as the global industry, I think has to work harder to be able to address. The recent UN Secretary General's Critical Energy Transition Minerals sort of report actually advocated for a global mining legacy fund to be set up precisely to deal with that type of problem. I've certainly advocated that for myself for many years. I think in Australia we've got the example of the Mining Legacy Fund in the Northern Territory, which is a policy that was put in place to actually deal with remediating and rehabilitating these old mines, these historic mines that were causing problems, including some modern mines that weren't managed well, actually. So if we do that, I think we'd get much better social acceptance of mining, right? And we need to be transparent, and I think that's one thing is a fundamental part of how we move forward in this area. Is we need to have not only good regulatory criteria in place, but the governance has to include very very high standards of transparency. And so whether it's on the environmental monitoring side, whether it's on the baseline side before mines are developed, looking at the social side of all of these types of things as well. So we need to make sure that when we are developing new mines in Europe, that's part of that conversation. Is we need to make sure we are actually doing it with modern regulatory requirements, and making sure that we understand where communities are coming from. Taking care of your own patch, your own local area is an important part for any community. So that's entirely legitimate. We need to demonstrate that that's actually what will be achieved, and that's part of the, I suppose, the challenge at the moment for Europe, as it is for many parts of the world actually.
That's a great advice. Now we're going to another big topic, and that's recycling. What specific steps can recycling play in addressing demand?
Recycling is basically an additional supply. So if we're looking at the policy language around this globally, like we typically call it the circular economy, and people think that sounds easy. You just recycle and everything gets around in a nice circular loop. It's not that easy, and it never has been. But we
Yeah.
can get there depending on the metal. If we're looking at lead, lead's already effectively a circular economy for most parts of the world. And that's been driven because it's just largely a single-use metal these days. It's lead is mainly used, almost principally used in lead acid batteries. Because of its toxicity, we've removed it in all sorts of other uses, such as paint or fuel additives and so on. But being a single-use product makes it easy to set up the policy. But also, batteries, because lead is toxic, it's required to be recycled. And so that means that in most parts of the world now, you've got lead being recycled at about 90 to 95%. So a lot of our current lead being mined is largely new stock being added to the system to meet demands for things like combustion vehicles and with batteries and so on. But um, when you're looking at other things, whether it be say iron or copper, in the UK we don't have a secondary copper smelter. So we have to whatever we recycle and we collect for recycling is exported elsewhere, and then we buy back either the products that contain copper, or we buy back copper products directly. So I think when we're looking at recycling, the policies sort of vary enormously, but um, the things we need to make sure of are the infrastructure. Do we have the different process plants and the collection, the logistics, the regulatory requirements in place? But also, when we're thinking about something like iron, there's at least 3,500 alloys of iron, often some really high value or specialty use, different alloys, whether it be for chemicals or for say high temperature environments or things like that. We don't want to be recycling in a way where we're just putting it all into one big pile, because that effectively cross contaminates those specialty alloys and you lose the value of those specialty alloys. Now, there are researchers and companies have been working on this for a long time. So we need to make sure that when we're looking at recycling, we are actually aligning all of these types of technical issues together. And that's where I think for some metals or products, for example, we're still evolving and working out how to do that much better. For electronics, for example, we now have the WEEE, the Waste Electrical and Electronic Equipment regulations that exist across the EU. They're also here in the UK. And so we collect a lot of that. But again, we may strip out some components like batteries, for example, but a lot of that is still shredded and then exported elsewhere for processing. So I think when you're looking at recycling, it's certainly a very important part of the overall picture. But the reality is quite complex. It depends on the products, it depends on the elements, and largely when we're looking at mining, we're dealing with one, two, three, maybe four or five elements. So mining has developed processes and does things on a very large scale at a single site. When you're looking at recycling, A smartphone has 60 elements, right? And so it's distributed. It's therefore very dispersed as a product, and so we have to have the collection systems. And when we're thinking about collection systems, that also means not only just the different transfer centers or other places to actually collect, but the consumer behavior. And so we need to make sure that consumers understand that when their phone has reached their end of life, they actually take it to their, say, recycling center, or they take it back to the retail place where they bought it. So I think there's
Yeah.
various ways that we can look at that, and put policies or processes in place to help achieve better rates of recycling. Um, but it's a very complex sort of web to really map together. And so it's I guess everywhere it's still evolving, it's still working out how to do this a lot better. But certainly from a very simplistic point of view, recycling is an important part of the supply. And depending on the metal, we're already doing pretty well. And I think one of the things in Europe, for example, under the Critical Raw Materials Act, is it sets some good targets. All right, and so that way, whether it's for copper or for other things, and certainly we're close to achieving some, and others we've still got a long way to go. But that's the direction we know we need to head.
How can we better track and quantify the material content in products to enhance recycling efficiency and supply chain transparency?
When you're looking at, I suppose, making sure we understand the products, and what materials, where they come from, and so on, there's various ways people are looking at that. One is blockchain technology, to look at the entire supply chain and make sure that's certified. Other technologies or processes include things like a passport to verify that, yes, that material has come from whether it's a responsible mine through various stages in manufacturing to eventually get to a product. Other parts of that, I think that we have to make sure of, is fundamentally transparency. So, and when you're looking at entire supply chains, I think mining is probably one of the most transparent parts of the supply chain in general, because we've got really good data on supply chains, also primary supply from mining. Once you start getting into the various stages of manufacturing, through the chemical processing, through component manufacturer to final product assembly, the amount of data publicly available to verify all of those types of things is very, very minimal. So typically, that's where the great problems are, is making sure that whatever product, we have to capture the entire supply chain. And when you're looking at many smelters, for example, many refineries around the world that process metals, they might get their concentrates from 10 or 20 different mines across multiple countries. So when you're looking at the zinc that comes out of a particular, say, refinery, it may not necessarily have just come from one mine or one country. So there's a lot of complexity in all of those types of things. But we can do that, and people are working on it, and it's something that I think it's an evolving area. But there are some good ideas out there, and I guess we're starting to see some of those sort of being implemented, such as, say, a battery passport, or or the use of blockchain. But I think we'll see a lot more evolution in that space in years to come.
There's a discrepancy in price between recycled materials and freshly mined ones. Um, how can we overcome this problem? How can we encourage companies to still use recycled materials even though they are more expensive?
Well, part of the problem there is when we're looking at it, and I suppose a simple hypothesis that's certainly been driving my research for ever since I started, is that mining is done on a very large scale, so it has economies of scale, and therefore mining is cheap. So the prices for mining
Yeah.
metals, but we're not factoring in the environmental impacts as much as we should. Those environmental costs, those social costs. All right. So we need to make sure that mining is actually properly accounting for all of those types of things. And that would make mining more expensive. Right. But would also mean we can say mining is being more responsible and actually not causing some of the long term legacy problems that we see from historic mines. Now, recycling, because of the nature of recycling, it's typically more dispersed. You've got to pay for the logistics of collection. And it's only recently we've started really working out processes to actually recycle products much more efficiently. So recycling tends to be more expensive, right? But it's paying for everything as part of what it's doing. So I think that that's certainly part of the problem. But part of the solution is mandating recycled content. Right. So when you're looking at a battery, for example, we could mandate a certain percentage of recycled lithium. Now, at the moment, that would be hard because we don't have a lot of a large scale of lithium recycling compared to, say, what we do with lead acid batteries and recycling lead from those types of batteries. But these things are a transition. It's not something you just suddenly flick a switch and everything it just magically happens. When we're looking
Yeah.
at examples of recycled content, look at paper. It took years for recycled content of paper to be able to get to the point where companies could say, "Yeah, this is 100% recycled paper," or plastics. We're looking at some products that are 100% recycled plastics. If you're looking at some of the different smartphone companies out there, uh, they actually have a policy of making sure that some components are produced from recycled materials to the greatest extent they can, and often they can actually achieve 100% sometimes. All right, so I think mandating recycled content is an important part of the solution there. But also, I think consumer education and sort of the broad sort of policy spectrum there to make sure that we've got the recycling infrastructure there, consumer behaviour, make sure that they're supporting these types of things as well. We can't make these things work unless consumers are dropping off the say the products after they're at the end of their life. But also looking at different industries and the way all of that works as well. So, and as I say, there are some good examples out there, but I think we've still got a long way to go, and we're evolving in that space for quite some time.
That's still a great suggestion. Are there viable alternative materials or technologies to reduce dependency on critical metals?
Not really, I think why we call things critical is largely because we're worried about their supply. Right
Yeah.
now, for a lot of the technologies, they have such complex materials and a lot of engineering and research over many years to actually achieve the sort of performances that we kind of take for granted, really. Whether it's our laptops, whether it's our phones, or increasingly in our energy systems as well. So I think it's not just about I suppose the shortages or other issues like that. It really comes back to some of the they're critical because we're worried about the supply chains and we're worried about the economic impact if we don't have access to good, reliable sort of supply. So I think for me, it's not just about alternative materials. Um, I think it's really addressing the critical materials head on in terms of those supply chains and looking at that from a global perspective.
How essential is global collaboration in managing resource extraction and distribution?
I think global collaboration is essential, and it's something we do. Maybe not necessarily as much as we would like, but um, I think these are global problems. Whether it's climate change, whether it's the energy transition, whether it's even just the sustainable development goals. I think there are various ways to look at it. I think we need better global collaboration. I think in some ways we've left it open to the sort of the free market, and markets are not perfect. And when we look at prices, prices are not always the best indicator of things. When we're looking at some sectors, you could look at um, uranium would be a classic where we have a spot price for uranium, and yet the actual amount of uranium that's traded through the spot price would actually be about 5%. So that is not a great indicator of a market. So let alone that markets can be sometimes near monopolies, near or duopolies, and so we can see those sorts of problems playing out in all sorts of different metals and minerals. So I think when we're looking at it, we know we need better global collaboration, right? And that way we can get our diverse supply chains. We can increasingly make them more responsible, and so that we're not just repeating problems that we've caused in the past by mining. Collaboration is fundamental to all of that. I think the questions become is how do you achieve that and how do you transition that when there's so much geopolitical competition and tension, really. And I think that's
Yeah.
one of the great
Yeah.
challenges that certainly well above my pay grade.
So, in that context, what strategies can accelerate the construction of the required renewable infrastructure?
The sort of policies that people are looking at come back to whether it's the energy targets, whether it's looking at things like recycled content, um, making sure that a lot of our different trade partnerships um, are in place, and so we understand the supply chains, linking that to the various manufacturing sort of sectors across, whether it's across the EU, whether it's in the UK, for example, or looking at other parts of the world as well. So I think it's really we have to look at every option, every way of approaching this. But um, we know we need to actually move forward and solve it. It's climate change and everything else is so important that we have to make sure we do that.
What research areas need to be explored further to find solutions to these challenges?
I think there's a variety of things. One is supply chains and making sure that we can better understand supply chains because they're very complex. It takes an enormous amount of work to actually unpack even just a single commodity, whether you're looking at the rare earth supply chain or lithium and others. It takes a lot of work to unpack all the different stages of a supply chain, right? To by the time something gets into a product, for example. So certainly a lot of research work needs to go on to making sure we can better understand supply chains and get hopefully some more transparency in there so we can um, quantify them and make sure we've got that demonstrated sort of reliability in the supply. Other areas are sometimes looking at different technologies, looking at say, well, there's always a role for looking at new technologies, whether that's in batteries, whether that's in the generation. And I think one of the areas that we're seeing some really great sort of evolution. If you're looking at the energy return on energy invested in a lot of renewable energy technologies, they're going up all the time because of that investment into the research. And as we make them we're making a lot of different renewable energy technologies, such as solar panels and wind turbines, on an increasingly larger scale. They're becoming more efficient. And so the energy cost to make them is going down and the power of them is going up. So the energy return on energy invested is now actually really strong compared to what it used to be. So I think it shows you that good investment into research into the technologies, I think, does pay off. But it's a long game, and it's something that we need to make sure we keep that commitment up, for the long term. So they're all the types of things that I think we need to keep doing, um, and making sure that we don't forget things like the geology. Like we've got decades and decades of resources known in the ground for every metal I've ever looked at, and I have published across most of the periodic table over the years. There's still a few gaps I'll get to, but what we can say confidently is when we're looking at the trends of production over time and resources over time, and where they're heading, there's still a role for good exploration and really good characterization of our existing deposits, and potentially even going back to old tailings and saying, well, we processed that for gold. What about going back for tellurium? What about going back for selenium, perhaps, or other elements that may be present that weren't extracted before? And we could do that in old, lead zinc tailings or copper tailings, potentially even iron ore tailings, where you go back and say, well, what's the potential for things like rare earths, for example? So I think that's another area where we should be investing in good research because, and that also a way we might be able to go in and clean up a whole bunch of sites too. So by going back, reprocessing, and there's certainly companies out there that are really investing heavily in this space, and I think are the early movers and certainly the leaders. But uh, there's a lot of good ways I think we need to make sure we look at the whole supply chain from the geology, mining through smelting, refining, and manufacturing to the products and end use. So I think we need to make sure we keep the investment in the research and innovation, across that whole spectrum.
You just raised another question. Can you comment on the potential of geologic hydrogen?
What we know at the moment is there's certainly some instances where geologic hydrogen's been found, but natural hydrogen, as it's often called, is something that
Yeah,
we're really just starting to look at. So I think the potential at the moment is impossible to say. All we know of is that there's certainly examples being found around the world, but hydrogen itself is something that I think you have to use it pretty quickly. Generally, like, it's something that you
yeah.
use locally. All right, now whether that be manufactured hydrogen for green steel, for example, whether that be other purposes, but so I think the the potential is out there, and it's worth some research money. I think we need to make sure we're not forgetting that we need to fund other research areas as well, whether it be the technology, the geology of critical minerals, all of those types of things. But certainly there's potential there, but exactly what that potential is, I don't think we really know enough at the moment to be confident.
Due to the fact that it's being researched these days, can we say it was kind of overlooked? And are there any other elements on the periodical table that are being overlooked?
Hydrogen, I think, was overlooked, but it's something that we didn't have a very large scale use for. We've never really developed,
Yeah,
I suppose, the need for much hydrogen, except in a very niche application. So, um, and that may change in the future with, say, fuel cells or things like that. But certainly, if you're looking at the periodic table at the moment, there's very few elements we don't mind, and scandium would be one that I think is probably it's going to have its day soon. It's starting to be produced, or it is now being produced in the Philippines at the two nickel laterite processing plants there. Um, and so it's basically a byproduct to the nickel and cobalt there. It's also being produced as a byproduct from titanium operations in Quebec now, in Canada. So historically, scandium had such an extremely small use that no one ever really worried about it. Because why would manufacturers develop a demand for scandium when there was no supply? And the age-old chicken and egg problem. Why would miners develop a
yeah,
supply when there's no demand? And so it hasn't crossed that threshold yet that we've seen, where once the demand starts to emerge, um, then miners will start to provide that supply. Historically, one of the best examples of that is nickel, because the Canadian nickel companies, especially International Nickel Company or INCO, invested a lot in its early days, in the first few decades of its operations in the early 1900s, into research and development on using nickel in steel alloys and stainless steel especially. And so that research and that investment actually created their demand, right? And so they were able to then gradually expand to the point where, certainly during World War One and World War Two, Inco was fundamental. And so Canada had a 80%, 90% near monopoly on nickel production for the best part of 50 years globally. And no one worried about that, of course, because it's Canada. They're nice people and the supply was very reliable. So nickel was not considered critical in the way that we would now consider, critical minerals, as when one country is so dominant like that, and especially one area like Sudbury. So, so I think investing in the R&D that's always a really good historical example of the value of that. Now, once they had that investment and they created that demand, of course, that then justified increasing their supply very significantly. We've seen similar patterns, and certainly Trevor Sykes and other scholars have documented this very, very well, where we've seen these patterns of breakthrough, whether it's aluminium or nickel and others. So I think scandium is probably one of the ones that's going to be next to sort of go through that pattern, where we see the a demand emerge, especially for aluminium scandium alloys, where it's very super lightweight and strong, and so that's being preferred by the aerospace industry, for example. So um, others, probably hard to say. Like hafnium has a small demand, but not likely to change too much. Unless there's a significant change in the way that nuclear power evolves, and that's not looking likely at the moment, except in particular countries. So renewable certainly seems to be the way the world is going, and so I think at the moment, we'll it's. I think we're certainly using most of the periodic table. There's not much left that we're not using.
iron has been identified as a critical mineral for the first time globally. What are the implications of this designation for industries and policies?
Well, largely, when we do a criticality assessment, like we've just released for the UK, it's a risk assessment. It's basically identifying those metals, minerals, materials that are at greater supply risk, and therefore those that could potentially cause, if there was a supply disruption of whatever sort. Um, it could be an environmental impact, such as a tsunami causing impacts on mine production. It could be civil unrest. It could be trade policies. It could be all sorts of ways we see a supply disruption, manifest, I guess. Then we have to look at the economic impact of that. And so when you're looking at something like iron, it has such a widespread use. It's used in the
Yeah.
construction sector. It's used in automotive. It's used in aerospace. It's used in lots of different products. So that means it has a very, very high economic value. And so now iron typically is generally supplied very well globally. But that's changing. And as much as we've got 1 billion tons a year coming out of Australia, you've got 300 or 400 million tons a year coming out of Brazil, and a large chunk in China. Um, of course, when we're looking at that, and the way that we've chosen to actually assess risk is using the product of that global supply and that economic vulnerability. And that means that when you're looking at iron, that product of both the global supply risk, and global supply risk for iron is much lower than, say, the rare earths or cobalt. It has a huge economic value and therefore vulnerability. Right? And that means that it effectively comes out as similar to lithium and titanium in its overall risk, i.e. criticality. Now, that's important because governments then say, well, if stuff is labelled or designated as a critical mineral, policies are therefore put in place to help address that. And so, which is why I think we're seeing a lot of mining companies out there, and especially in the exploration space, they like to be listed that yes, they're exploring for lithium, they're exploring for cobalt, or they're exploring for rare earths, because if it's designated as critical, that means there's government policies, and that often means funding opportunities or other mechanisms that can help support their activities. And that's probably as it should be. Like, we need to make sure that if we're worried about the supply and that potential impact, then obviously we need, as was it the UK, was the EU, and elsewhere, we need to make sure we've got policies in place that deal with that. Now, for iron, what those policies are, I guess that's something that the UK will now start to look at and go forward. We know we've shut down our last blast furnace here in the UK. It'll be a few years now until we get a new electric arc furnace online. And in some ways, that's actually good for a circular economy, because an electric arc furnace uses scrap materials as feedstock. But we come back to the question of, well, there's lots of different alloys of iron. We can't just mix them all up. So we need to really understand the different alloys, the flows, where those stocks are. There's a lot of work to do to really unpack that. And certainly the iron sector has been doing this for a long time anyway, and they've been good
Yeah.
at recycling. And iron does have a reasonable recycling rate overall compared to some elements. But I guess that's the nature of the problem, is that iron is one of the most valuable materials we use, and so it therefore the way we've decided to assess criticality, it means that iron is now a critical mineral, and that we can't forget that just because it's a widely supplied material globally and widely used, um, that still means it can be critical.
Yeah. What lessons can we learn from past supply disruptions to enhance resilience in critical mineral supply chains?
When we look at the history of supply disruptions, they can come about from all sorts of different reasons. Some for civil unrest, as we saw in the Congo in the 1980s, 1990s. Others are from trade barriers or export quotas, such as China implementing extremely strict rare earth export quotas in 2010 that sent the rare earth price absolutely sky high. So part of that is funding alternative supplies, making sure that we're not just reliant on one country or one company, perhaps. That it's not always necessarily easy, because developing new mines is not always easy either. So when we're looking at the responses, it's looking at basically all of the above: recycling, the potential for substitution, product design, looking at
Yeah.
the regulations, and so on. Sometimes regulations can actually be a barrier, where they can actually disincentivize things like recycling. So when we're looking at things, because we call something waste, it gets treated as waste under waste regulation. So rather than calling something a waste, maybe we should be looking at it as a raw material that we can then reprocess through recycling to actually make sure we can get the elements out and then reuse them and recycle them more fully. So when we're looking at the solutions in this space, it's basically all of the above. We look at the regulations, we look at recycling, we look at product design, we look at the different materials, where we're mining them, all of these types of things. And that's typically, when we're looking at the examples of supply disruptions, that's what all of them end leading to, is making sure, that's what we keep coming back to, is that all of these solutions will depend on the also different types of supply disruptions, but we still need to come back to these basic approaches.
Yeah. How do we address the trade offs and challenges involved in establishing a circular economy for critical materials?
Not easily. it part of the problem is that everything is moving so fast. So our technologies are evolving, and we've seen that especially in the electric vehicle space in the last 5 years, where there's been a huge increase, which in many ways not many people saw coming, of lithium iron phosphate batteries really taking over as the pretty much a dominant battery type now for electric vehicles. So now, there's still a large fraction of nickel, manganese, cobalt type lithium batteries used in electric vehicles. Um, so I think the sheer pace of change and evolution is always a problem. And so um, part of it, I guess, is always making sure we're monitoring those types of changes, right? And so we're building our policies and adapting as quickly as we can to make sure that whether it's from a recycling point of view, whether it's from a product design point of view, the regulations. All right, so I think the things like the Critical Raw Materials Act, like having targets for things like recycling and the amount of mining in Europe and so on, setting targets, I think we're always much more likely to get closer to those targets or exceed them than if we don't set targets. All right. I think it also comes back, I suppose, to one's attitude to life. I think, if you set yourself a basic sort of target or just sort of plod along, all you've done
Yeah.
is plod along. If you set yourself a strong target, a stretch target, that's tough to meet, you're always much more likely to do much better, I think, overall. So I think that's the overall approach we typically need to take with critical minerals, and look at all of the different aspects, because it's a very complex problem. And we've got products like our electronics that integrate 60 elements. And so we have to think about not just iron on its own, but we have to think about all of those 60 elements. And that means the whole complexity of modern technology and the way that we approach our policies and everything else. And so that it means that there will be trade-offs sometimes. So um,
Yeah.
and we just have to make sure we understand what those trade-offs are, right? And then choose wisely as best we can.
In what ways can substitutions in material usage alleviate criticality risks? And what are the associated trade offs in performance and cost?
If we've seen in the past, the cobalt example is probably one of the best ones, where when cobalt, price went sky high after civil unrest in the Congo in the late 1970s, the aerospace sector substituted, and so they developed different alloys for their use now, and that reduced their need for cobalt, right? And that was successful, and that worked. And now you're looking at other examples. You've got lithium iron phosphate as substitution. Um, and that was also to reduce the need for cobalt, which is a very expensive component for batteries. So I think material substitution can be important. It's not always easy to make happen. All right, it takes time. So sometimes you know I suppose it's just something you've just got to keep open eyes to, really. But it's there are other examples of substitution. When we're looking at electronics, for example, we're seeing the decrease in the amount of gold used, and that's largely due to the price more than substitution, probably. All right, so very expensive component in electronics. But so I think substitution can help. Right, it can certainly alleviate a supply risk. But the challenge is that often we've designed materials and developed them to achieve that level of performance. And so uh, often what we see in the substitution space is that when we do substitute, you do get lesser performance. Now, sometimes that may mean you can still make the product, or it's
Yeah.
maybe cheaper, so it maintains a sort of cost competitiveness. But there is sometimes trade-offs between that sort of cost and the performance and so on. But it's why we always need to make sure we're keeping funding into research and development, because that's the way we can innovate to achieve, sometimes find a new material that actually does achieve either the same performance or better. So, but it's a long game. Yeah, substitution is
Yeah.
always a
How do you foresee AI and advanced data analytics contributing to the exploration, efficient use, and supply chain management of critical materials?
I don't think we fully know the answer to that yet. I think what we're seeing is that there are examples of AI being used in mineral exploration. So we can see, and certainly whether it's some of the work that's going on at the British Geological Survey here, or similar groups elsewhere around the world, where AI is being used to, I mean, when we say AI, that also means techniques such as machine learning to
Yeah.
analyze, large data sets, and finding patterns in data sets that haven't been found before. So there's that type of thing, and that's important work. Other things are, I suppose, analyzing supply chains and finding data sets, and so on, and building things. But um, certainly from our own experience, uh, and looking at the literature, the training data sets that are used for AI are absolutely fundamental. And so if you don't have a good sort of open, a data set to really train your AI with, you're always at risk that the output you're getting from AI may not be as good or as accurate as you need. So I think there's still evolution to go in the AI space, but now whether it's also looking at product design, making products more materially efficient so they can achieve the same service, the same output with less materials. So the AI probably has a good role to play there. And looking at the different materials as well, like using AI to design new materials. People are certainly doing that too. So I think there's a lot of things that AI could potentially be used for, and I don't think we really know what the full spectrum of that is yet, or how successful and how quickly AI will be. Um, but certainly, as we've seen the rise of AI very quickly in recent years, we can probably expect that there will be a lot of evolution very rapidly in coming years. I think that's probably a fair statement.
Yeah. What about the potential benefits and challenges of using automation and robotics in extraction and processing of critical minerals?
The mining industry has been increasing their use of automation over the long term, like over decades, and now it's sort of, I suppose, accelerating much more rapidly lately. Um, but there are already autonomous vehicles, like autonomous haul trucks, being used at mines in different places around the world. So I think there's certainly some good evolution there, and maybe that will also help with improving safety outcomes as well. Like certainly, autonomous vehicles are certainly more resource efficient. They can tend to drive, in more direct lines and things. So and of course they're using the accelerator and brakes much more efficiently when they're driving. So, I think there's certainly really good examples of automation already actually out there in mining. I think the other combination that I think we will increasingly see is not only just the automation, but then the electrification of mining. And I think those two things combined will see a great transformation in mining over coming years, because once you've got automation, you've got electrification, and I think that's the technology is already there. Right? I think the next questions become where's the energy coming from, i.e., the electricity, and that for many parts of the world, you've got such as the Pilbara in Australia, certainly no shortage of sunshine. So there's great opportunities there to provide, let's say solar systems, solar farms that then power mining, that help with the automation and so on as well. So I think that's sort of some of the trends I think we'll certainly see. But there's already good technology out there, and it's evolving very, very rapidly.
That's always good to hear. What specific steps can industries take to adapt their design, manufacturing processes, and stockholding strategies based on criticality assessments?
Oh, that's a tricky question. In some ways, I think it's understanding what are the technologies that are being rolled out now. It's also understanding where technology is heading, and that can be difficult. I think anyone who's going to be confident about EV battery chemistry in the next, beyond the next 10 to 20 years, is a brave person. What we can say is we know for the next decade, things will still most likely, but maintain a dominance with lithium. Now, there may be other battery chemistries come in, whether it be sodium based or others. All right, but exactly what type of lithium battery? Well, that's hard to predict even for the next 10 years. So I think a lot of it is just understanding the different technologies that are being rolled out, whether it's electric vehicles and the associated drivetrains and batteries. Right, the drivetrains, of course, being reliant on rare earths, but that's not the only way we can make batteries. Oh, sorry, drivetrains. We can also make drivetrain magnets, the permanent magnets, out of other materials, whether it be strontium and so on. So, so I think it's keeping an eye on on what are the trends in the key technologies such as drivetrains, batteries, solar panels. If we're seeing things like cadmium telluride solar panels roll out, then obviously we need to be thinking about where that cadmium and where that tellurium is coming from. Now, they're both byproduct metals, and we've got really good data for cadmium and generally reasonable data for tellurium as well. Right. So we're pretty confident we can supply things like cadmium and tellurium to support the rollout of things like cadmium telluride type solar cells. But then you've got other types of solar cells as well, whether it be the SiG cells, the copper, indium, gallium, and selenium cells. So I think part of it is just really coming back to the basics, that the way we've always done things when we're looking at this space. It's understanding what the technologies are, understanding what the future is, right, and seeing where those opportunities are. And that's how you get an Apple. That's how you get a Google, or you get a Tesla, for example, is seeing those future opportunities and then working towards them. So I think, and there's many examples, and certainly this is exactly what China's done. They've built their positions in these supply chains. They've worked hard to get to sort of the position they're in. So, um, and to the point now globally where they've got such dominant positions in so many things, there's a lot of geopolitical tension about that. So, so I think what it comes down to, if we look at the UK, for example, if we were to start mining lithium in the UK, and there's a few ways we could do that. We've got hard rock deposits. We've also got geothermal energy, where the brine, the very salty water associated with that geothermal, also has lithium in it. So so we could be providing not only hard rock lithium, but also geothermal derived lithium. And then potentially, if we build the recycling sort of infrastructure and so on, we can provide lithium that way as well. Now, if we did all of that, we would probably see lithium become less critical. Now, whether it would still be labeled a critical mineral or not, it depends on what happens globally and the economic value and all of those types of things. But um, ideally, if we've got the resilient supply chain, then that means that something is no longer critical, and that's actually a good thing. That's what
Yeah.
we're working to achieve, because we want that resilient and sort of a reliable sort of supply chain that supports our economic activity, that supports the policy goals we have, such as net zero, the sustainable development goals, all of these types of things. So I think that's the sort of the broad spectrum, I guess. It's the devil's always in the detail, whether it's the technologies and all of those types of things.
Yeah. And in that context, finally, looking ahead, what do you see as the most significant emerging challenges and opportunities in the field of critical minerals, and how can we prepare to address them?
I think the greatest challenge really is making sure we do have those diverse and resilient sort of supply chains globally. And that means sometimes that we do have to move away from some countries in favor of others. Now, and that creates geopolitical tension right there as well. So now, and that's not just about China as well. There's other countries. We could look at South Africa. We could look at other countries like Russia, for example, where the issues are different. Now, obviously for each of them, but to me, that's the great challenge. Now, the opportunity is that we need to do that in a way that actually adds value. And that's the great challenge of policy. And that's certainly, I suppose, the role of government. The work we do at the Critical Minerals Intelligence Centre is the analysis and the data synthesis that underpins basically what is now designated as critical. And then it's up to the UK government, of course, to then move forward on what that means in terms of policy. But ultimately, it comes back to the same things. It's making sure that the opportunities are to actually look at, well, where are the policy opportunities? What can we do differently uh, to help solve some of these problems, to achieve things such as net zero, the energy transition, and things like that. So I think for every problem, there's always opportunity. I guess that's certainly the way I look at it, and I think that's what we need to do. Is we need to say, right, where are the different deposits around the world? Geologically, we know that for almost everything, right? So then we can say, right, well, where are the opportunities to develop either new mines? Where can we develop? Where is the better places to develop new smelters and refineries, or the different manufacturing stages? Because when we're looking at electric vehicle, you've got the batteries, you've got the drivetrains, you've got the chassis, you've got all the electronics that are in an increasing part of every car as well. That's the sort of opportunities we need to start to look towards, and then obviously develop the policy to achieve all of that. So, and we go from there.
Gavin, thank you so much for this insightful interview and for being my guest today.
My pleasure.
Looking to amplify your brand in the hydrogen energy sector? Welcome to H2 Energy News, your go-to platform for impactful industry insights. Every month, we connect with over 80,000 visitors and generate more than 251,000 page views. Our reach is unmatched, with over 1.2 million web impressions and a loyal social media following of 9,000 plus. Our newsletter reaches 77,000 plus subscribers, decision makers, industry leaders, and innovators. Want to target specific markets? Our geo-targeting capabilities cover Europe, the United States, and the MENA region. We reach key stakeholders, 27% senior executives, 32% directors, and 20% owners and partners. H2. Energy News isn't just a news platform, it's where the hydrogen energy community converges to shape the future. Join us and let's make an impact together. Visit energynews.biz and take your brand